All right, listener, ready to dive into some physics? Today we're tackling a college-level physics exam.
And we're not just going to skim the surface. We're going to break down those problems step by step, really get into the concepts. Think of it like your own personal physics cram session.
You brought a stack of practice problems, everything from stars and springs to, oh, I see some rotational motion in there too. This will be fun.
Yeah, it's pretty comprehensive, which is great for us. It means we can hit on a lot of the big ideas in physics.
So where should we start? What's the first problem that jumps out at you?
How about something with a little cosmic drama? Let's talk about binary stars. Problems 1 and 2 on this practice exam give us a glimpse into how those celestial objects dance around each other.
Okay, so two stars with the same mass. We have their initial positions, the forces acting on them, and we know star B's initial velocity.
Right. And problem 1 asks us to find, roughly speaking, star B's velocity after 1 hour. Now, here's the catch, that gravitational force between them. It's not constant. It changes as the stars move closer or further apart.
So it's not like those simple projectile motion problems where everything's nice and neat.
Nope. We got to think about how that force is constantly evolving. So we're going to need to use what's called the position update formula. Basically, it tells us the final position is the initial position plus the average velocity multiplied by the change in time.
Makes sense, but if the force is changing, how do we find the average velocity?
We can be a bit clever here. Over a tiny, tiny time interval, we can assume the force is essentially constant.
Okay, so we're breaking down the problem into these teeny tiny steps where we pretend the force is constant. I like it. So what do we do with that force?
First things first, we use Newton's law of gravitation. You know, that good old force equals g times the product of the masses divided by the distance squared.
And all those values, they're all given in the problem, right?
Yep. Now with that force, we can go to Newton's second law of motion. Force equals mass times acceleration. Rearrange that, and we get the acceleration of star B due to gravity.
So we've got the acceleration. What's next?
Now we figure out how much star B's velocity changes over that tiny time interval. Change in velocity is just acceleration times change in time, and our time interval here is 1 hour, which is 3,600 seconds.
So we add that change in velocity to the initial velocity, and there you have it, the approximate velocity after an hour.
You got it. Now, problem 2, it takes us a step further. Wants to know the new position of star B after that same hour, and guess what? We use that position update formula again.
So final position equals initial position plus the average velocity times the change in time.
Exactly. Plug in those numbers, and you've got star B's new position after an hour of this gravitational dance.
You know, it's kind of wild to think that even though we're talking about these massive stars and these huge forces, the changes in velocity and position over an hour are pretty small.
Yeah, right? Really puts things in perspective. Space is vast. Even small forces can lead to big changes over cosmic timescales.
Yeah, absolutely mind-boggling.
Okay.
Let's bring things down to earth now, literally. Problem 4 throws us right into the pool, so to speak, with a buoyancy problem.
Buoyancy. That upward push you feel when you're in the water. This one's about a cork suspended underwater by a string. It's all about density and volume.
Okay, so how do we even start to figure out all the forces going on here?
Well, think about it like this. For that cork to be held in place, all the forces acting on it have to be in balance.
Like a tug of war.
Exactly. Buoyant force pushing up, and that's got to be equal and opposite to the cork's weight pulling down, plus the tension in that string pulling down too.
Okay, so how do we find each of those forces?
Let's start with the buoyant force. Archimedes' principle tells us it's equal to the weight of the water displaced by the cork.
Makes sense. The cork pushes the water out of the way and the water pushes back, right?
Exactly. To get that weight, we need the volume of the cork, which is also the volume of water displaced. Now remember density. Density is mass divided by volume, so we can rearrange that to find the volume.
Got it. Mass of the cork divided by its density gives us the volume.
Precisely. Now multiply that volume by the density of water, and then multiply by the acceleration due to gravity. Boom, you've got the weight of the water, which is equal to the buoyant force.
Okay, so we've got the upward force. And since the cork isn't moving up or down, we know that upward force has to be perfectly balanced by the downward forces.
Right, so we set up an equation. Buoyant force equals the weight of the cork plus the tension in the string.
And to get the weight of the cork, it's just the mass of the cork times gravity.
You got it. Now you can just rearrange that equation and solve for the tension.
Tension equals the buoyant force minus the weight of the cork. We're like physics detectives, huh?
That's a great way to put it. And the best part is, it's not about memorizing some crazy formula. It's about understanding the principles.
Okay, ready for another dynamic duo. Work and energy. Problems 6 and 8 on this practice exam really show how those two are intertwined.
Yeah, they're perfect for this. Let's start with problem 6. Imagine you're pushing 2 boxes across an ice rink. One box is stacked right on top of the other.
Sounds simple enough, but there's got to be a twist.
There is. The question asks for the work done by the lower box on the top box. So how are those boxes interacting? That's the key.
The lower box isn't pushing or pulling on the top box directly. It's just moving forward because we're pushing on it.
But think about this. For that top box to stay put on top of the lower box, there's got to be something keeping it from sliding off.
Friction. That's got to be it.
Right. It's the friction between those two surfaces that keeps them moving together.
So the frictional force is what we need to think about when we're calculating the work done by the lower box on the top box.
Exactly. And because the boxes are moving together, the friction is static friction.
No relative motion between the surfaces.
Right. And if there's no displacement between the surfaces, then the work done by that static frictional force is
0. It's kind of counterintuitive, isn't it? I always thought friction meant work was being done.
It can be tricky. But in this case, the lower box does no work on the top box, even though they're both moving.
Physics is full of surprises. So the answer to problem 6 is 0. All right, what about problem 8? It seems like we've got a spring, a mass, and someone slowly lowering that mass until the spring is holding it at rest.
Yeah, this one asks how much work you do in that process.
Okay, seems straightforward enough. You're applying a force, moving that mass, so work is being done, right?
Well, you're right that work is being done, but remember, it asks specifically about the work you do. You're not the only force acting on that mass. There's gravity pulling it down, and then there's the spring force pulling it up.
Oh, right. It's not just about my effort. It's about all the forces involved.
Exactly. To figure this out, we can use something called the work energy principle. It basically says that the total work done by all the forces acting on an object is equal to the change in the object's kinetic energy.
Okay, but hold on. That mass starts from rest, and it ends at rest.
Right.
Its kinetic energy doesn't change at all.
Exactly. If the change in kinetic energy is 0, then the total work done by all those forces must be 0 too.
Interesting. So we have you pushing down, gravity pulling down, and the spring pulling up. How do we break down the work done by each force?
Well, remember, work is force times displacement, but the direction matters. If the force and the displacement are in the same direction, the work is positive. If they're in opposite directions, the work is negative.
Okay, so your work is negative because you're pushing down and the mass is moving down. Gravity's also doing negative work. What about the spring force, though?
That's the interesting one. Initially, the spring isn't stretched, so it's not doing any work. But as you lower that mass and the spring stretches, it starts pulling upward against the motion.
So the work done by the spring force is positive because it's opposing the direction of motion. And since the total work has to be 0, all those individual works have to add up to 0.
Exactly. If we know how far you lower the mass and the spring constant, we can figure out the work done by the spring. And from there, we can rearrange our equation and find the work you did.
It's like solving a little physics puzzle.
It is. And that's what makes physics so cool. Okay, ready for a spin?
You mean angular momentum?
Yep. Problems 15 and 16 bring us into the world of angular momentum. We've got a rotating wheel and a lump of clay. Classic physics scenario.
Sounds fun. I'm ready to get spinning.
Yeah.
Problem 15 is all about analyzing different statements about angular momentum. But before we jump into that, maybe a quick refresher on what angular momentum actually is.
Of course. In simple terms, angular momentum is the measure of an object's tendency to keep rotating. Like, you know how linear momentum is all about an object moving in a straight line? Angular momentum is about spinning.
Okay, so if something has a lot of angular momentum, it's really determined to keep spinning.
Exactly. And there are two main things that affect it. The object's moment of inertia, kind of like its rotational mass, and its angular velocity, which is how fast it's spinning.
So a heavier object would have more angular momentum, and so would an object spinning really fast.
Precisely. Now, armed with that knowledge, let's tackle those statements. The first one says that the angular momentum of the device plus clay, like right after they collide, is equal to the angular momentum of the device plus clay right before they collide.
So it's saying angular momentum is conserved. It stays the same even when things are changing.
Exactly. And the principle of conservation of angular momentum states that if there are no external torques acting on a system, the total angular momentum stays constant.
And torques are like rotational forces, right? They cause things to start or stop spinning.
You got it. And in this problem, the axle of the wheel is frictionless, meaning there's no external torque. So what do you think? True or false?
Well, if there's no external torque, then angular momentum must be conserved, which means statement 1 is true.
Excellent. Okay, statement 2 says the angular momentum of the falling clay is 0 because it's moving in a straight line. What do you think about that one?
This one is a little tricky. It is moving in a straight line, not spinning or anything.
You're right to be cautious. Here's the catch. Even though the clay itself isn't rotating, it still possesses angular momentum relative to the wheel's axis of rotation.
Wait, so even if it's moving straight, it can still have angular momentum?
Yep, because it has the potential to cause the wheel to rotate once it sticks. Think of it like this. The clay as a point mass is moving towards the edge of the wheel. Even though it's moving straight, it will make the wheel rotate when it hits.
Okay, I see what you mean. So statement 2 is false. It does have angular momentum, even though it's moving in a straight line.
Exactly. Now, statement 3 claims that just before the collision, the angular momentum of the wheel is 0.
They can't be right. The problem says the wheel is initially rotating counterclockwise. If it's rotating, it has to have angular momentum, so false.
Absolutely. Moving on to statement 4, it says the angular momentum of the device is the sum of the angular momenta of all 8 balls attached to it.
That seems logical. Each of those balls is part of the wheel, so they each have their own angular momentum, right?
Precisely. You need to add up all their contributions to find the total angular momentum of the device. So, true.
Okay, great. What about the final statement? It says the angular momentum of the device itself is the same before and after the collision.
This one requires a bit more thought. We know the total angular momentum of the whole system. The wheel and the clay is conserved because there are no external torques. But that clay adds mass to the system, right? And it changes how the mass is distributed.
And that affects the moment of inertia. So even though the total angular momentum is conserved, the angular momentum of just the device will change.
Exactly. So statement 5 is false. This problem really highlights how important it is to be super precise with our language in physics.
All right, on to problem 16. We need the expression for the magnitude of the angular momentum of the combined system right after the clay hits the wheel.
So basically right after they become one spinning unit. And remember, angular momentum is conserved, so the total angular momentum right after the collision is the same as right before the collision.
So if we find the angular momentum of the wheel and the angular momentum of the clay before they collide, we can just add them together.
You got it. So let's start with the wheel. We know its angular velocity is omega, but to calculate its angular momentum, we need its moment of inertia too.
And we can figure out the moment of inertia of the wheel because it's basically 8 balls evenly spaced out.
Right. And the moment of inertia of a point mass, like one of those balls, is just its mass times the square of its distance from the axis of rotation.
And the distance from the axis to each ball is L2. So the moment of inertia of each ball is its mass times L2 squared.
Exactly. And there are 8 balls, so we multiply that by 8 to get the total moment of inertia of the wheel.
Okay, so to find the angular momentum of the wheel before the collision, we multiply that moment of inertia by omega. What about the clay?
For the clay, remember, it is moving in a straight line, but it still has angular momentum relative to the wheel's axis. Its angular momentum is its linear momentum times the perpendicular distance from its line of motion to the axis of rotation.
And that perpendicular distance is L2 times the sine of 45 degrees, because that's the angle between the clay's path and the radius of the wheel.
Exactly. And the sine of 45 degrees is just 1 divided by the square root of 2.
So the clay's angular momentum is its mass times its velocity times L2 times 1 divided by the square root of 2.
Precisely. Add that to the wheel's angular momentum, and you've got your final expression for the total angular momentum right after the clay hits the wheel.
Wow, we just derived a whole equation. This is making me feel like a real physicist.
You're doing great. You're starting to see how all these pieces fit together. Now, how about we step onto a spinning platform and experience some angular momentum firsthand?
You mean problem 17, the one where I'm part of the experiment. Let's do it.
All right, let's see what happens when you start changing your moment of inertia.
So picture this. I'm standing on a spinning turntable holding two barbells with my arms outstretched. My friend gives the turntable a spin, and then I pull the barbells in close to my body, and guess what? I start spinning faster.
It's the classic ice skater move. And it's all about conservation of angular momentum. When you bring those barbells in, you're changing the distribution of mass, which directly affects your moment of inertia.
So when my arms are outstretched, the barbells are farther from the axis of rotation, which means my moment of inertia is bigger.
Exactly. It's like trying to spin a big, wide object takes more effort. But when you pull your arms in, you're bringing that mass closer to the axis of rotation, making your moment of inertia smaller. Like going from spinning a wide object to spinning a more compact one.
But the problem mentions that the barbells don't contribute to the angular momentum when they're pulled in close. So do we just ignore them completely?
That's an important detail. It means we're focusing only on the change in your moment of inertia, not the barbells. Once they're in close, they're basically part of you for this calculation.
Got it. So how does this all tie back to conservation of angular momentum?
Well, remember the principle, if there are no external torques messing things up, the total angular momentum stays the same.
And I'm guessing we can assume this turntable is frictionless, so no external torques.
Exactly. So as your moment of inertia decreases when you pull the barbells in, your angular velocity, your spin speed, has to increase to keep that total angular momentum constant.
That's why I spin faster.
Right.
Okay, so the problem asks us to actually calculate my approximate moment of inertia.
Right. And we actually have all the information we need to do that.
Right.
We know your initial and final angular velocities, the mass of those barbells, and how far they are from the axis of rotation when your arms are outstretched.
So using the formula for angular momentum, we can set up an equation where the initial angular momentum equals the final angular momentum.
Exactly. On one side, you have your moment of inertia with arms outstretched times the initial angular velocity. And on the other side, your moment of inertia with arms pulled in times the final angular velocity.
Okay, but we have two unknowns there, my initial and final moment of inertia.
True, but we can express those in terms of your body's moment of inertia and the moment of inertia of the barbells.
So my initial moment of inertia is my body's moment of inertia plus the moment of inertia of the two barbells when my arms are out.
Exactly. And the moment of inertia of each barbell is just its mass times the square of its distance from the axis of rotation.
Got it. We can plug that into our equation. What about my final moment of inertia?
Remember, the problem said the barbells don't contribute once you pull them in. So your final moment of inertia is basically just your body's moment of inertia. We can ignore the barbells at that point.
So we can plug that into our equation too. Now the only unknown is my body's moment of inertia.
You got it. And you can solve for that with a little algebra. Just plug in all those known values. The angular velocity is the barbell mass and the distance, and you'll get an approximate value for your body's moment of inertia.
Wow, that's impressive. We just figured out my moment of inertia. Okay, ready for more angular momentum fun?
Bring it on.
All right, let's tackle problems 18 and 19. Looks like we have a barbell spinning on a fixed axle, but this time there's a force being applied.
So now we're adding in some external forces. This will be interesting.
Problem 18 asks us to find the barbell's angular momentum, L. Luckily, it gives us everything we need.
It does. Two small balls, each with a mass of 1 kilogram, connected by a rod we can consider massless, spinning at 10 radians per second clockwise.
Okay, so to find angular momentum, we need moment of inertia and angular velocity. And we have both.
Yep. Since the barbell has two balls of equal mass at equal distances from the center, we can treat them as point masses for calculating the total moment of inertia.
So we double the moment of inertia of one ball,
Right.
which is just its mass times the square of its distance from the axis of rotation.
You're getting the hang of this.
And then to get the angular momentum, we just multiply that moment of inertia by the angular velocity, which is 10 radians per second.
See, piece of cake. Okay, now problem 19 throws a wrench in the gears a bit, introduces a force acting on the barbell. We need to find the rate of change of the barbell's angular momentum.
Okay, so things are getting a little more complex. I know forces can cause changes in motion, both linear and rotational.
You're right. And the key concept here is torque. Torque is like the rotational version of force. It's what causes those changes in angular momentum. In fact, the rate of change of angular momentum is equal to the net torque.
Got it. So we have to figure out the torque caused by this force.
Exactly. And torque is calculated using something called the cross product of the force vector and the position vector where the force is applied.
Okay, the problem tells us the force is -100 newtons in the x direction, and it's acting at a point with coordinates medico 0.3 meters in the x direction, 0.4 meters in the z direction, and 0 the z direction. So those are our force vector and position vector, right?
Yep. Now, don't worry too much about the actual cross-product calculation. The key is to understand that it gives you a vector that's perpendicular to both the force vector and the position vector.
And the magnitude of that resulting vector is the magnitude of the torque, right?
Precisely. In this case, since the force is in the x direction and the position vector has components in the x and y directions, our torque vector will point in the z direction.
So that means the rate of change of the barbell's angular momentum will also be a vector in the z direction.
You're getting it. And the magnitude will be equal to that torque we calculated.
Okay, I think I'm starting to wrap my head around the connection between forces, torques, and how angular momentum changes.
It's a beautiful interplay of concepts. Now, let's shift gears a bit. Problems 20 and 21 take us back to something familiar. A block in free fall.
Free fall. That doesn't sound very rotational.
That's what makes it interesting. It challenges us to think about the angular momentum of something that's not actually rotating.
Okay, you have my attention. So problem 20 asks for the angular momentum of the block about a point A that's off to the side of its path. But how can it have angular momentum if it's just falling straight down?
Remember, angular momentum isn't just about spinning. It also depends on an object's linear momentum and its distance from the point we're considering for rotation.
So even though it's not rotating on its own axis, we can still think about its angular momentum because it's moving along a path that's a certain distance away from point A.
Exactly. And to calculate that, we use the same formula. Angular momentum equals linear momentum times the perpendicular distance from the line of motion to the point of rotation.
Okay, so the block's linear momentum is just its mass times its velocity, v downward. And the perpendicular distance is just that horizontal distance, x, between the block's path and point A.
You got it. Now, angular momentum is a vector, so we have to consider the direction, too.
Right. Let me do the right-hand rule. Fingers point in the direction of the velocity, which is down. Curl them towards the perpendicular distance, which is to the right. My thumb is pointing into the page.
You nailed it. The angular momentum vector points into the page. Okay, now problem 21 asks for the rate of change of the block's angular momentum about point A. What do we need to think about for this one?
Well, we know the rate of change of angular momentum is equal to the net torque. But in this case, the only force is gravity, right? Is the torque just constant then?
Good question. And this is where it gets a little tricky. Remember, torque is the cross product of the force vector and the position vector. And even though gravity is constant, that position vector, which points from point A to the block, that's changing as the block falls.
Oh, I see. So even though gravity is constant, the torque isn't. It changes as the block falls.
Exactly. And because the torque is changing, the rate of change of angular momentum is also changing. To calculate it at any moment, we'd need to find the specific torque at that instant.
This is wild. It's amazing how even a simple falling block can get pretty complex when we're thinking about angular momentum.
It is. It shows you how physics is all about understanding those fundamental principles that govern motion, linear and rotational. Okay, ready for a collision.
Bring it on.
Problem 22. We have a bullet striking a rotating cylinder. This one's going to combine what we know about linear and angular momentum and conservation laws, too.
Okay, so a bullet's fired horizontally at a certain distance above the axis of a cylinder. The cylinder is initially at rest, but then the bullet embeds itself in the cylinder, causing it to rotate. And we're trying to figure out the bullet's initial speed. Where do we even start?
The key here is to remember that both linear momentum and angular momentum are conserved in this collision, assuming no external forces are messing things up. So we can use those conservation principles to set up equations.
Okay, so first, linear momentum. The total linear momentum before the collision has to equal the total linear momentum after the collision.
Right. Beforehand, just the bullet has momentum because it's moving. The cylinder is at rest.
And afterward, the bullet and cylinder are stuck together, moving as one. So their combined momentum is their total mass times their final velocity.
Exactly. They're moving as one, so they must have the same final velocity. So you can set up an equation. The mass of the bullet times its initial velocity equals the combined mass times that final velocity.
Okay, so that's one equation. But we have two unknowns, the bullet's initial speed and the final velocity of the combined system. This is where angular momentum comes in, right?
Right. Again, we can use conservation of angular momentum to make another equation.
So just like linear momentum, the total angular momentum before equals the total angular momentum after.
Exactly. Now, before the collision, the cylinder has zero angular momentum because it's not moving. But the bullet, even though it's moving in a straight line, has angular momentum relative to the cylinder's axis of rotation.
Just like that clay hitting the wheel.
Uh.
Even though it's moving straight, its distance from the axis gives it angular momentum.
Exactly. The bullet's angular momentum is its linear momentum times that perpendicular distance from its path to the cylinder's axis, and that distance is given in the problem.
Okay, so we can calculate the bullet's initial angular momentum. What about after the collision?
After the collision, the bullet and cylinder are rotating together. Their combined angular momentum is their moment of inertia times their angular velocity.
And the moment of inertia of that whole thing is the moment of inertia of the cylinder plus the moment of inertia of the bullet, right?
You got it. The moment of inertia of a cylinder rotating about its central axis is just 12 its mass times the square of its radius. And the moment of inertia of the bullet, now embedded in the cylinder, is its mass times the square of its distance from the axis.
Okay, so we can calculate the moment of inertia, but we still don't know the angular velocity after the collision.
True, but remember our first equation from conservation of linear momentum. It relates the bullet's initial velocity to that final velocity of the bullet cylinder system, and we can use that final velocity to figure out the angular velocity.
Oh, right. Linear velocity and angular velocity are related. If we know the linear velocity of a point on a rotating object and its distance from the axis, we can find the angular velocity. In this case, the bullet's final linear velocity is the same as the linear velocity of a point on the cylinder's edge.
Perfect. Now we can substitute that expression for angular velocity into our equation for conservation of angular momentum. So now we have two equations, two unknowns, the bullet's initial velocity and the final velocity of the combined system.
We can solve for both. It's amazing how we can use these conservation laws to figure out such a complex problem.
Right. It really shows you how physics can connect seemingly different ideas. Okay, ready for problems 23 and 24? Looks like we're going to test our equilibrium skills.
Equilibrium, like balancing forces. I'm ready.
These are great problems for understanding static equilibrium, the conditions for an object to remain at rest. We have a uniform rod attached to a wall by a hinge, with the other end supported by a cable.
It's like one of those classic physics diagrams.
It is, and problem 23 asks us to find the tension force in that cable. We need to consider all the forces acting on that rod and make sure they're all balanced out.
It's all about balance, huh? Okay, so what forces are we working with here?
We've got the tension force from the cable, the weight of the rod itself, and the force exerted by the hinge.
The problem says the hinge lets the rod rotate freely in the xi plane. What does that tell us about the hinge force?
That's a crucial detail. It means the hinge can exert both horizontal and vertical forces on the rod, but it can't exert a torque.
Oh, right, because the hinge is the pivot point. Any force going directly through the pivot won't cause it to rotate.
Exactly. Now, to find the tension in the cable, we can use the fact that the net force in both the x direction and the a direction has to be 0.
Okay, so in the x direction, we have the horizontal component of the tension force pulling to the right and the horizontal component of the hinge force pushing to the left. They have to be equal to cancel each other out.
Perfectly explained. What about the a direction?
We've got the vertical component of the tension force pulling up, the weight of the rod pulling down, and the vertical component of the hinge force, which could be either up or down depending on the situation.
Right. And those have to add up to 0 as well.
Okay, so we have two equations, one from the x direction, one from the a direction. But we have three unknowns, the tension force, and those horizontal and vertical components of the hinge force. Can we even solve for all that?
We need one more equation. That's where the net torque being 0 comes in.
Ah, right. For equilibrium, the sum of the torques about any point has to be 0.
Exactly. And to make our lives easier, we can pick a point to calculate torques around where some of the forces act directly through it, which means their torque is 0. Any ideas?
The hinge. Since both components of the hinge force act through the hinge, their torques are 0.
Great thinking. Now, the only forces that contribute to the torque about the hinge are the tension force and the weight of the rod.
And the torque due to each force is just the force times the perpendicular distance from its line of action to the hinge, right?
Right. But remember, we need to pay attention to the direction of the torque, too. Clockwise torques are negative, counterclockwise are positive.
Okay, so the weight of the rod acts at its center of mass. That'll create a clockwise torque, which is negative. And the tension force acts at the end of the rod and creates a counterclockwise torque.
Exactly. And for the rod to be in equilibrium, those two torques have to balance out. Their sum must be 0.
That's our third equation. Now we have 3 equations and 3 unknowns. We can solve for everything.
We did it. And problem 24 builds on this by asking for the magnitude of the vertical force exerted by the hinge on the rod.
But we already solved for that. We just have to look back at our solution from the last problem.
You got it. That's the beauty of solving these equilibrium problems systematically. Once you have all the forces, you can answer any question they throw at you.
Okay, this is making me feel like a physics master. But let's keep this rotational momentum going. Problem 25. We've got a pulley, a string, a constant force, and a challenge to figure out how fast the pulley is spinning after 2 seconds.
This one's a great way to see how rotational dynamics, the study of rotating objects, ties in with the concepts of force, torque, and moment of inertia. It's all about understanding how forces make things spin and how we can predict that motion.
All right, so we have a pulley, basically a disc with a string wrapped around it. Someone's pulling on the string with a constant force, and that makes the pulley rotate.
You got it. We're going to use the rotational version of Newton's second law of motion to analyze this. Remember, the linear version tells us force equals mass times acceleration. Well, the rotational equivalent says that the net torque on an object equals its moment of inertia times its angular acceleration.
Okay, so instead of force and linear acceleration, we have torque and angular acceleration.
Exactly. And just like a force causes an object to speed up or slow down linearly, a torque causes it to speed up or slow down rotationally. So first things first, what's the net torque acting on our pulley?
That torque is coming from the force on the string, right?
Right. That force creates the torque that makes the pulley spin.
And torque is calculated by multiplying the force by the perpendicular distance from the line of action of the force to the axis of rotation. So in this case, that distance is just the radius of the pulley.
Exactly. Torque equals force times the radius of the pulley.
Got it. What's next?
Now we need the pulley's moment of inertia.
Ah, right. Moment of inertia. That's like a measure of how resistant an object is to changes in its rotation.
Precisely. And it depends on the object's mass and how that mass is distributed. The problem tells us that the moment of inertia of a disk about its center is 12 times its mass times the square of its radius.
Okay, so we've got the torque and we've got the moment of inertia. Now we can use that rotational version of Newton's second law to find the pulley's angular acceleration, right?
You got it. Angular acceleration is the rate of change of angular velocity. So once we have that, we can figure out how much the pulley's speed changes over time.
And to connect angular acceleration to angular velocity, I think we need those rotational kinematic equations.
You're right. They're very similar to the ones we use for regular linear motion. In this case, we can use the equation that says final angular velocity equals initial angular velocity plus angular acceleration times time.
And the pulley starts at rest. So the initial angular velocity is 0.
Perfect. To find the pulley's angular speed after those 2 seconds, you just multiply the angular acceleration we calculated by the time 2 seconds.
Amazing. We just figured out how fast the pulley's spinning.
And we did it by connecting force, torque, moment of inertia, angular acceleration, and angular velocity. It's beautiful how it all comes together.
It's like seeing the same physics principles at play, but in this whole new spinning dimension. Okay, problem 26 looks like more forces, torques, and angular acceleration. Bring it on.
This one's a great test of how well we understand how forces create those torques and how those torques make an object rotate.
So we have a rod that can rotate around point A, which is at one end. Then there's a force, F1, acting at the other end, making an angle theta 1 with the rod. And another force, F2, acting at the center of mass of the rod, making an angle theta 2 with the rod.
Right. And just like before, we're going to use that rotational version of Newton's second law net torque equals moment of inertia times angular acceleration.
Okay, so we need to figure out the net torque from those two forces, and then use that along with the rod's moment of inertia to get its angular acceleration.
Exactly. Remember, each of those forces is going to contribute to the total torque. And the torque from a force is the force times the perpendicular distance from the line of action of the force to the pivot point, in this case, point A. And remember, those directions, clockwise torques are negative, counterclockwise are positive.
Got it. So first up, F1, the force at the end of the rod, its perpendicular distance to point A is just the length of the rod, L. And it's pushing down at an angle, so that'll create a clockwise torque, which is negative.
Right. The magnitude of that torque is F1 times L times the sine of the 2 on.
Okay, now for F2, the force acting at the center of mass.
For that one, the perpendicular distance to point A is L2 because it's acting right in the middle of the rod. And it's also pushing down at an angle, so it creates another clockwise negative torque.
So the torque from F2 is F2 times L2 times the sine of the theta.
Exactly. Now, to get the net torque, we just add those two torques together.
So it's negative F1 times L times sine of theta 1 plus negative F2 times L2 times sine of the theta.
Perfect. Now, for the rod's moment of inertia, the problem tells us the moment of inertia of a rod about its end is 13 times its mass times the square of its length.
Great. We've got the net torque, we've got the moment of inertia, plug them into our rotational Newton's second law equation, and solve for the angular acceleration.
You make it sound so easy. It's great to see you connecting all these rotational concepts. Now, how about a quick conceptual break? Problem 27 brings us back to the playground, the classic seesaw.
A seesaw. Sounds fun.
This problem is a great example of how those simple ideas of balancing forces and torques actually play out in the real world. And it's a good chance to practice our understanding of equilibrium without getting too lost in calculations.
All right, so we have two people with different masses, M1 and M2, on a seesaw. And they're balanced perfectly. It's an equilibrium.
Right. And for equilibrium, two conditions have to be met. The net force acting on the object must be 0, and the net torque acting on it must also be 0.
Okay, so let's start with the net force. We have the weights of the two people pulling down
Yeah.
and the normal force from the pivot point pushing up. Because the seesaw is balanced, the normal force has to perfectly counteract the combined weight of the two people, right?
Exactly. Now, for the fun part, the net torque. This is where their positions on the seesaw come into play.
The problem says person 1 with mass M1 is a distance D1 from the pivot point. We need to figure out how far away person 2 with mass M2 has to be to keep it balanced.
Right. And remember, torque is force times the perpendicular distance from the force's line of action to that pivot point. And we have to be careful about the direction of the torque, too.
So if we imagine person 1 on the left side of the seesaw, their weight would make a counterclockwise torque, which is positive. Person 2 on the right would make a clockwise torque, which is negative.
Exactly. For the seesaw to be perfectly balanced, those torques have to cancel each other out. Their sum must be 0.
So we can write an equation. The weight of person 1 times their distance, D1, plus the weight of person 2 times their distance, D2, equals 0.
You got it. And weight is just mass times gravity, so we can rewrite that as m1 times g times d1 plus m2 times g times d2 equals 0.
And then we can rearrange that equation to solve for D2, which is the distance person 2 needs to be from the pivot to keep everything perfectly balanced.
It's amazing how something so simple, balancing torques, can explain something as familiar as a seesaw.
Right. Physics is everywhere. Okay, I think things are about to get a bit more intense. Problems 28, 29, and 30. A bullet, a hanging stick. Sounds like we're in for some action.
These problems are a great example of a multi-step problem where we need to use multiple physics concepts to really understand what's going on. It's like a physics puzzle.
All right, challenge accepted. Problem 28 sets the stage,
Ugh.
asks which principle or principles we need to use. So we've got a stick just hanging there vertically. A bullet comes in, embeds itself in the bottom end of the stick, and then the stick swings.
Upward, right. So we've got two key events here. First, that collision between the bullet and the stick. Then the swinging motion afterward.
So for the collision, we'd use conservation of momentum.
Exactly. When that bullet hits and embeds itself, they move together as one. That means their momentum has to be conserved. And since the bullet's sticking, it's an inelastic collision, so kinetic energy won't be conserved. But linear momentum, always conserved in collisions, as long as there are no external forces messing things up.
Okay, momentum's on our list. What about that swinging motion after the collision?
That's where conservation of energy comes in. As the stick swings up, its kinetic energy is changing into gravitational potential energy.
But it's not just moving up, it's rotating too,
Right.
right? So we have to consider both translational and rotational kinetic energy.
Exactly. And because of that rotation, we'll also need conservation of angular momentum to analyze how it's spinning.
So we need all three. Conservation of momentum, conservation of angular momentum, and conservation of energy. That's a lot to keep track of.
It is. It's like a physics trifecta. But don't worry, we'll break it down step by step. Now, problem 29 asks us to find an expression for the angular speed of the stick, with the bullet embedded right after the collision.
Okay, so we're focusing on that instant right after they become one. And we're dealing with a collision, so conservation of angular momentum is our tool here, right?
You got it. The total angular momentum of the system just before the collision has to be the same as the total angular momentum just after.
So before the collision, the stick's just hanging there. no angular momentum, but the bullet, even though it's moving straight, does have angular momentum relative to that pivot point at the top of the stick, right?
Right. Just like we talked about with the clay and the wheel. To calculate the bullet's angular momentum, we need its linear momentum and the perpendicular distance from its path to that pivot point.
So the bullet's angular momentum is its mass times its velocity times the length of the stick.
Exactly. Now, after the collision, the bullet and the stick are rotating together as one. Their combined angular momentum is their moment of inertia times their angular velocity.
And to find the moment of inertia of this new bullet stick system, we have to consider both the stick and the bullet, right?
Right, again. We need the stick's moment of inertia about its end, which is 13 times its mass times the square of its length, plus the moment of inertia of the bullet, which is its mass times the square of the length of the stick.
So we can set up an equation where the bullet's initial angular momentum, which we already figured out, equals the combined angular momentum right after they stick together.
Precisely. And from that equation, we can solve for the angular speed of the stick with the bullet embedded.
Okay, so we've tackled the collision. Problem 30 wants us to figure out how high the stick swings after the bullet hits. So now we switch gears and think about energy.
You got it. Conservation of energy is key for understanding the stick's motion after that collision. The kinetic energy it has right after the bullet hits is going to be transformed into gravitational potential energy as it swings up.
But it's not just moving upward, it's rotating too, right? So we have to factor in both types of kinetic energy, translational and rotational.
Exactly. The translational kinetic energy is just 12 times the total mass times the square of their velocity, and rotational kinetic energy is 12 times the moment of inertia of the system times the square of the angular speed.
And all that kinetic energy is converted into potential energy at the highest point of the swing.
Right. Because at that highest point, the stick momentarily stops moving, so all the kinetic energy has become potential energy.
And potential energy is mass times gravity times height. So we can set up an equation where the total kinetic energy right after the collision equals the potential energy at that highest point.
Exactly. But we don't know the change in height of the stick. That's what we want to find.
So how do we connect that change in height to something we do know, like the angle the stick swings up to?
A little trigonometry will help us out here. If we let theta max represent that maximum angle, we can express the change in height as the length of the stick times 1 minus the cosine of theta max.
Okay, so we substitute that expression for the change in height into our energy conservation equation. Now we have an equation with just one unknown theta max.
You got it. And we can solve for that to find the maximum angle the stick swings up to after the bullet hits.
This problem was a marathon. We used conservation of momentum for the collision, conservation of energy for the swing, and even threw in some angular momentum and trigonometry.
It really brings together a lot of different physics concepts, but that's what makes it so satisfying to solve.
We covered a lot of ground in this deep dive: gravity, stars, buoyancy, work, energy, momentum, angular momentum, and even some rotational dynamics. It's amazing how it all connects.
It really shows the beauty and elegance of physics. And to our listener, we hope this exploration has not just given you some answers, but also a deeper appreciation for the laws that govern our universe.
Remember, physics isn't just about formulas and equations. It's about understanding those fundamental principles behind the formulas and learning to apply them to real-world situations.
And most importantly, it's about the joy of discovery, figuring out how things work and seeing those connections between different ideas.
We didn't have time to cover every problem on this practice exam, but hopefully this deep dive has given you the tools and the confidence to tackle the rest.
With a little practice and a lot of curiosity, anyone can become fluent in the language of physics.
And who knows? Maybe you'll even discover some new physics of your own. Until next time, keep exploring, keep questioning, and keep diving deep into the wonders of the universe.